What is up, guys? I'm back here with another video. It's been a really long time since I've made one, but I'm going to talk to you a little bit about the support vector machine SVM algorithm and how it works exactly. So in this situation, suppose we have cats and dogs. The green dots here represent cats, purple dots represent dogs, and we're looking at their height and weight. So, and our goal is to create a line, if you will, that best classifies and best separates the cat and dog. So there's so many ways we could draw this line. Looking at it, we could draw it here. We could actually, maybe not that many ways, but we could do that. We could do something like that. There's so many different ways we could draw this line. And that's exactly what SVM does, is it finds the optimal line that best separates the data between classes. So there's this thing known as margin. So when we create a line, this is probably the best line we could create looking at it. But when we create a line, we look at the margin. So, and margin is the distance between these points, these data points here, and the line. And these little points here that we're drawing the line to, like we're factoring in their distance, these little data points here, these are known as the support vectors, because they're supporting the algorithm's decision-making process and making that line the line. Hence the name support vector machine. So if we look, this is what that line looks like now. And the important thing to keep in mind here is we want this margin to be high. We actually want the distance between these dots and the line to be as high as possible. Right, and not only do we want it to be as high as possible, we want it to also be balanced between classes. Like the distance between the green points and the line overall should be about the same as the distance between the purple points in the line. So if you look, that is probably a pretty well done boundary. Now with the brown here, I will create a boundary that's maybe less effective, where these purple points have, almost have not that high of margin, whereas these green dots have like a giant margin. Look like that. That would be an example of a really poorly done line, a really poorly drawn decision boundary. So that is something we don't want. Now there's also what we call some hyperparameters to the SVM. These include, hold on. These include C and gamma. C and gamma. So when gamma is low, it means that when we draw this line here, we take into account the margin of we take the distance of the support vectors, we take them into account further out. So that doesn't really make a lot of sense, but let me just draw a line to explain what I'm talking about here. That was a really bad line. Let's try it. So what happens is the distance here gets measured between all the support vectors. So with a low gamma situation, we're going to look at like all of these guys, all these support vectors out here. Okay. taking them all into account when we determine how to draw our line. So ironically enough, that's when gamma is low. You take more higher ratio of the data points into account, right? However, when gamma is high, you're only taking, I'll use it round for an example, you're only taking into account like the closest support vectors. And what this does is, if you can imagine, okay, this looks very neat. These data points are very neat, but if you can imagine, if it was kind of more squiggly looking, let's say we're like, you know, and like, let's just zoom in on a class. Pretend we're like zooming in. We're like kind of zooming in on a boundary, right? So then you got this, and it's kind of flows in. It's kind of wonky. It's not really like a perfect separation. But let's pretend we've got like way more data points back here, and we got way more data points back here. So if we have a really high gamma, that means we're only taking those data points into account. The line could look more something like this. But if we look at all the data points back here and all the data points up here, we might see in the grand scheme of things, or in the bigger picture, that's not really that big of a deal. And we may draw a more reasonable line like that and allow for some misclassification to take place for, you know, generalizing to the data as a whole. So that is what gamma does. And what C does is C determines how it essentially boosts the accuracy of the model. So C is another of those C is another of those things where if we have high C, we're going to, you know, draw the line very much tailored to the actual data. So we may draw something like, let's make this gray so it looks a little more distinguishable. We may draw something kind of like this, you know, trying to get every single data point right. So what C does, what's good about C is oftentimes, you know, the separation, the line of best separation is not some simple thing that you can just, it's not some simple line that you just draw. There is some nuance to it. It may have a little up and down here, it may have some curve to it. However, you know, and that makes the accuracy high. However, a lot of times what happens is, if C is really high, you'll create a model, it'll fit to the training data that you give it very, very well, get 100% accuracy. But then when you test it on data that's not like out on the testing data, the accuracy is going to go down because it's not really able to generalize to the data very well. So it's a trade-off between having something that's accurate and actually makes the classification properly, and having something that's too accurate in that it as they call it, overfits to the data set. So that is a little rundown on the algorithm, and just something I want to explain as to why this is a whole like algorithm that does this, and why we don't just do this, is because this was simple, because I was just showing you two-dimensional data so that you could visualize it. But the reality is that, you know, every feature that you have in the data set is another dimension. So you're often working with data that has like 10 or more dimensions. And there's really no way that a human can visualize something that's in 10 dimensions, right? So that is where this model comes into play, because it's able to create boundaries even when the data is in really high dimensions like that. Anyway, that's been the video, guys. Thank you so much for watching. And I'm not really sure what my plans are with this channel, but I definitely have like 2 more video ideas that I plan on making. So I hope to release those soon anyway. See you in the next one. Bye.